Okay, the next thing I'd like to talk about is the variance of a random variable. And then I'll discuss a little bit more about the mean of a random variable. So the variance sort of determines how spread out a probability distribution is. Okay, so in particular, so we can define the variance as follows. So the variance of a random variable x is defined to be var of x, which I'm defining, remember this means this equals sign means I'm defining to be equals, is the expected value of x minus its mean all squared. Okay, so what's that doing? I've got my, let's suppose my random variable lands at some point x, and then I look at how far away that random variable was from where I thought it was going to land, okay, with the average place that random variable would land. Okay, when I square it, that gives me some notion of this distance here from x to its mean. Okay, further, the standard deviation of x is the square root of the variance. Okay, so one way of thinking about it is sort of, I guess this isn't standard notation to write standard x, but sometimes people use it that way. Okay, it's really just to take the square root of this variance. Okay, now what's that doing? Well, you can sort of think that we've got, what we're doing is we're looking at the kind of the average of all of these distances. Okay, and this is sort of in squares, alright? Then we kind of need to convert it back to new money, okay? So the units aren't in terms of squares, but we take a square root, okay? So just like we think of the distance of, say, a triangle with the side A and B, then the distance at the length of this side is sort of a squared plus b squared square rooted. Okay, in some sense this is exactly the same sort of calculation we're doing, sort of giving an idea of the distance, okay, away of all of these points that the random variable x can take. Alright, so what the standard deviation and the variance are doing essentially is giving us some measure of how spread out the distribution is. Okay. One thing to add, it's really a notational thing, is that sort of the mean of a random variable is often, it doesn't have to be, denoted by mu and the standard deviation by sigma, and thus the variance by sigma squared. Okay? So often use the Greek letter mu for mean and Greek letter sigma for standard deviation. Okay, we don't have to define it that way, it's just a common notation that's used. Okay. Something that's a kind of useful way of representing the standard deviation. Okay, so rather than writing up as a sort of expected square of these different distances, okay, we can write it slightly differently. And many of you have seen this already, that the variance of x could be written as the expected square divided by the square of the expectation. Okay, so we can prove that, it's not too difficult. So we know the variance of x is equal to e to the x minus e of x all squared. Alright, so we're going to do the sensible thing whenever we see a square and expand out the brackets. So we're going to end up with x squared lots of this x, then 2 lots of x times this expectation here. Okay, then added on that expectation squared. Alright. Okay, and then what we can do is use the linearity of our expectation. Remember that if we've got a number of terms, it's the same as adding up the expectation of each of those terms. Okay, and notice as far as this x is concerned, it's been multiplied, this random variable has been multiplied by a constant that is minus 2 times this number, which I can think of as mu, or just as the expectation of x. Notice this is no longer a random variable, it's just a number that happens to represent the mean of x. Okay, so we get minus 2 lots of e to the x times the expected value of that random variable x. Okay, and then finally here, this is just a constant as far as this expectation is concerned. Okay, if I change omega, the expected value of x doesn't change. Okay, if I change the outcome. Okay. Alright, and what you can notice is this is really just 2 lots of this. Alright, and if that was a little bit short at some points in the middle, maybe try to do it with the sums. Okay, with the definition of sum x, p of x equals x in place of e of x. Just double check that you agree with me in terms of this calculation here. Right, so you can try and do it explicitly using sums, or you can try and do it with the expectation still here. Okay. So in other words, what we end up with is the variance. So to summarise what that says is the variance is the mean of the mean square, mean of the square, minus the square of the mean. Okay? Alright. One thing that I think is kind of more important than this fact is the following, that if we have 2 independent random variables, then if I look at the variance of x plus y, and this is just equal to the variance of x plus the variance of y, right? Right? So let's prove that quickly, and then I'll discuss a little bit. Okay? So, well, the variance of x plus y, we're just using our previous lemma, is just equal to the expected value of x plus y squared minus the expected value of x. Well, that's right, it's just the x plus y and then all of that all squared. Okay? Now, I can expand both of these out. Okay? So the first one, I'm going to get the expected value of x squared plus 2 lots of the expected value of x times y plus y squared. And from here, I'm going to get the expected value of x and then squared plus 2 lots of the expected value of x times the expected value of y. Okay, and then added that to the expected value of y squared. Right, and now I can put these together, and I'm going to get the expected value of x squared minus the expected value of x all squared, this and this, plus, let's look at the y terms, the expected value of y squared minus the expected value of y all squared, and now let's look at the x times y terms. We've got plus 2 lots of the expected value of x times y, then minus 2 lots of the expected value of x times the expected value of y. Okay, but we know that since these two are independent, x and y are independent, these two are going to cancel each other out. Right? So what we're left with is e to the x squared minus e to the x all squared, okay, which is the variance of x. Right? And then from this, we're just going to get the variance of y. Right? Now, that might seem sort of a semi-useful result, but I actually think it's quite an important result. Okay? Now let's think of it this way. If our standard deviation, okay, let's interpret this for a second. So our standard deviation of x, or of the random variable x, okay, is somehow a notion of our distance, a bit like we have, if we want to know the distance in sort of normal Euclidean coordinates, okay, that c is given by the squares of each of the coordinates square rooted, okay, so giving it sort of an idea of what is the distance of this shape c away from where it started from, 0, okay. So in some sense the standard deviation has the same role. It gives you an idea of how far that random variable has spread out around from its mean. Okay? So then you might begin to think, well, what if I add up a number of random variables together? Okay, so let's suppose I start to add up a number of coin tosses. Okay? So let's consider what the standard deviation is if I sum up, I don't know, some large number n of a number of, say, coin tosses. Okay, so I want to understand, if I do an experiment many times, how far away should the results of that experiment be from the mean? Okay. Now, I know that the standard deviation is really just the square root of the variance. Okay, so this is just the square root of the variance of of all of those individual experiments. Right? Now, we know from the rule above that if I have two independent random variables, I just end up summing them. And similarly, like before, if I had three random variables, I just end up summing their three variances, okay? All the way up to n, okay? So essentially, this is just the sum of the variances of all the experiments so far, okay? Now, assuming they're the same experiment, like throwing the coin, okay, the variance is going to be the same for all of those. So I'm going to get n lots of the same variance, okay? So I'm going to get n lots of the variance, which I could write as sigma squared, square rooted, okay? So in other words, we're going to get square root of n times sigma, okay? So if I start with the random variable x with the standard deviation of sigma, and I do that experiment many times, I expect the error to be about square root of n, okay? So let's say I do, I throw a coin 100 times, okay? I'm expecting an error of about the size of square root of 100, should we say, which is about 10, okay? Or if I throw a coin 1,000,000 times, okay, I'm expecting the error, okay, I should expect for 1,000,000 coin throws, I should get 500,000 heads, okay, and it should be give or take, say, 1,000, because that's the square root of 1,000,000, okay? So actually this gives you really good grip into the way that errors propagate in random systems, and this is something that's studied extensively and forms a lot of areas, okay? The way that lots of little errors can creep up and add together, okay?